So I believe you should have gotten the third week videos. So with that, so the second week videos form the core of data structures course. The third week are some sort of a miscellaneous advanced topics. First week is sort of building up to the core. Okay, so so people who are teaching or revising, they should get a good overview of the data structures topics from these 3 weeks, 13 sessions. And you need to complement if you really need details, because I have really done only an overview. So you need to complement those topics by detailed reading or lecturing on those things. Okay. Any questions or comments? So today I'm going to just spend time on going over the first problem sheet. Before that, anybody has any questions or comments? And maybe can somebody tell me whether you are listening to me, because I just want some response. You can hear me?
Yes, sir. Audible, sir. We are able to, sir.
Okay, great. Thank you. Okay. So any questions coming before I move on to the first problem sheet? Okay. So I plan to just do the first problem sheet. Then I'll do the next problem sheet next week. So this week I have not given any problem sheet because you still have some backlogs of the last 2 problem sheets, and also this material is somewhat advanced, whatever I've released. So yeah, okay. Okay, so let me see if I can just go to the first problem. The first problem says that, so all of them are pretty much, most of the questions require binary search, as you would have seen, because that's essentially what we had done in the first session anyway. So the first question says that I have an array, let's number them 0 to n minus 1, and the first n of them are positive. So this is positive, positive, and then you get negative numbers. And your goal is to find this n. You don't know n. Okay? So first part A says give me an order log n algorithm. I haven't seen your answers yet, but does somebody want to take a crack at this question and give me an answer? You can just sort of unmute and tell me a high-level idea of how the algorithm would go.
Sir?
Yeah, go ahead, sure.
So it's like first you check the n by 2th entry.
Which n? Which n? Capital N or small n?
Capital N.
Yeah, okay.
And check whether it is positive.
Mm-hmm.
If yes, do binary search in the second half of the array.
Not do binary search, I would say recurse on the second half, because we are doing slightly different, right?
Okay.
Apply the same algorithm on the second half.
Yeah, okay. So do recursion in the second half of the array.
Right.
If answer is no, then do recursion in the first half.
Exactly. Okay. So
repeat this until your n by 2 power k is less than or equal to 1.
When you say recurse, it captures everything.
Yeah.
That's
okay.
What recursion is. Until
complexity is order of log capital N.
Yes, until you have one element, you keep doing this. So the algorithm is see if we can. Algorithm will say, okay, so here is my array. I take the n by 2th element and compare, and there is no comparison, by the way, right? Unlike binary search, You are not comparing, there is no query element to compare with. All you are doing is check whether this is positive or not. Okay, you have to make these distinctions clear. It is like a binary search, but binary search, you have a sorted order and you're querying for an element. Here it's not like that. So I just check whether it is positive or negative. Suppose it is positive, then I am looking for, think of it as the smallest, the first negative element, because that gives me the n, or the location before that gives me the n. So first negative element is likely to happen on the right half, so it recurs. So if positive recurs on the right, else if it is negative, then you know that you don't know whether that's the first negative element. There may be something even negative before that. So I'm going to recurse on the left. That's it. Okay, so this is a fun, interesting problem, not necessarily binary search in the sense of you are given a sorted order and you are searching for a query element, but the idea is the same. You are just compare, and then all think of it as you are looking for the first negative element, because that's what that location is, what n is. Okay, so this gives me a log of capital N. Okay, good. Now, what about now the next question is more interesting. What I'm saying is, look, if maybe just first 10 numbers are positive, and but your array size is huge, maybe 10,000. Then you are doing log of 10,000. I'm saying, no, give me something which is order log of 10. It depends only on n. Okay, so that's the second part. Yeah, so that's the order of log of small n. Okay, so yes, anybody did this and has a suggestion how to go about doing this? So Vijayalakshmi ma'am, you haven't tried, or you didn't get it?
Actually, I thought that we are actually looking at the worst case. So
Yeah.
I thought the worst case is when your small n is equal to capital N. That will be the worst case.
Yeah, sure. But
In all positive.
I'm looking for a solution which is sort of parameterized by the small n. Okay.
Yeah,
So the
I
algorithm.
not get it actually.
Yes, in the worst case, it could be log of capital N. But I'm looking for some natural an algorithm which adapts itself to the size of small n. Okay. Anybody else? Any thoughts? Any ideas? So this, in fact, when I was driving, I actually thought of a real world application for this interesting thing, right? So I'm flipping through my FM channels, and maybe my FM channels has this, 91.1, 91.2, and so on and so forth. And I really want to zoom in on some channel, which I don't remember, maybe, 103.4 or something like that. So one way is to just go linear search, just do one by one. But then I found out that in the radio, they had some markers. So for example, they had 91.1, and then maybe, actually there was not even a 91. So it was, so they had actually 87, then 105, 120. These are some marker points they had kept. So I want to go to, let's say, 103. I can start from 87 and tune in a linear fashion one by one, or I could go to 105 and then come down slowly, get to my 103. Okay, so there were these marker in between things I could jump. Okay, so that's the kind of idea what I want to do. I want to find this n, this smallest negative number, but I don't want to do linear search. I have this, in fact, imagine the scenario where your capital N is not even known. That's actually this is an application for that scenario where you don't even know capital N. All you know is this huge unbounded array. I don't know the size, and somewhere numbers start becoming negative. Till that point, it's positive. So I have to somehow find that number. If I had known capital N, I can do this log capital N algorithm, but I don't, suppose I don't even know capital N. Okay. Now that I've given this hint, does anyone want to, any new ideas come to you? So again, let's look at, yeah. So the scenario is that I have this large array. Let's even say I don't even know the end. And here is the n, which I want to find out. Of course, once I go there, I know by looking at the index whether it's a positive or negative. So I know the value of that. But until that time, I don't know. So I mean, in fact, there are a lot of interesting puzzles around this time. Okay, around this problem. So I'll come to that. Okay, so it's like this, right? You have a mug, and you're told that, and you have a 1,000-story building, huge, tall, 200-story building, and you're told that this mug is strong enough that it will not break if you throw it from some nth floor, and after that it will break. You need to find n. One way to do it is to just keep throwing it from each floor and find the first floor where it doesn't break. That's like the linear search. But you can do some jumping, right? That's the idea. So somebody wants to take a crack? Based on what I just said, once I know if it breaks or not, I know. So similarly, once I check the location, I know whether it's a positive or a negative number. Okay. So I want to find the first negative number. Think of it that way. So one is linear search, one is this huge binary search where if I know the end of the array, suppose I don't even know the end of that array. What can I do?
So arbitrarily you check some 100th entry or something.
Okay. Okay. So okay, good start. So I start from first entry, and then maybe I go to 100th entry.
So if it is positive, then you go to maybe 200th entry.
200th entry. Okay. So I'm just doing some sort of, because I don't know my boundary, so I just keep doing this, right? So at some point, I get a negative number. Then I know,
then you come back.
Then you know that whatever I'm looking for is in this range. Okay. Good. So that's the idea. Okay. Right. So how much time will let's say if I do 100, okay, roughly how many steps I have done? So it will be, n is some number. So once you cross that n, you figure that out, right? So you will have 100, 200, 300, and then whatever. Suppose n is some between 100k and 100k plus 1, then you will do some k steps, right? So roughly, you will do something like n by 100 steps plus 100. The plus 100 is to do the second search in that range, right? Okay, is 100 the right way to do? What can I do? Right? That's the next question. Okay. So anybody else just jump in, throw ideas, no problem if they are right or wrong. I mean, this 100 idea was a good idea. So, but now we need to pin it down, and our goal is to do some order log n. Okay. So what we are going to do, this is what we are going to do. I'm going to start with searching at 1 location, location 2, location 2 square, 2 cubed. What am I checking? Checking whether it's positive or negative. Okay, so n is somewhere here. N is somewhere here. I'm going to do some 2 power k, and then maybe I'll do 2 power k plus 1. Then I realize, at 2 power, up to 2 power kth location it was positive. 2 power k plus 1th location is negative. So I know that my range, whatever I'm looking for, is in this range. Now I can do a binary search, because now I found a bounded thing. I can do a binary search. Okay, so this is my algorithm. Now let's carefully see how many comparisons have I made. Okay. So I made some k comparisons initially, right? Because I'm looking at 1, 2, 2 square up to power k, and maybe actually k plus 1. And then this range is 2 power k, because it's 2 power k plus 1 minus 2 power k is 2 power k. So here I'm going to do binary search, like your original binary search, and that is going to be another k, because it's 2 power k is the range. So this is the total time. Is the algorithm clear? Should I repeat? Anybody?
Can you please repeat, sir?
So what I am saying is, instead of this 100 idea, I'm going to do what is called doubling. This is called doubling binary search. So I look at the first location, check whether it's positive or not. If it's negative, good, I'm done. If not, I go to the second location, assume it's positive. I go to the fourth location, and then 8th location, and then 16th location. I'm doing this doubling and look for, whether it's positive or not. Okay. Remember, n is the first location where is the first negative. Let's say first negative or the last positive, doesn't matter. This is the first negative number. So at suppose n is between 2 power k and 2 power k plus 1. The n I don't know. Suppose the n is, every number is between 2 power I and 2 power I plus 1 for some I. Every number, any natural number is between some 2 power I and 2 power I plus 1. So when I come to 2 power kth location, it will say it's positive, and 2 power k plus 1th location will say it's negative if n is between 2 power k and 2 power k plus 1. So then I know that, so that my n which I'm looking for is in this range. And in this set of locations, number of such locations is actually 2 power k. Here I do my good old the part A binary search by just going to the middle and checking for positive, negative, and doing that. That binary search will take k steps, because it is the range is 2 power k. So the total number of comparisons or checks I have done is k plus 1 plus k. Okay, is that clear?
Yes, sir.
Okay, I can repeat if anybody wants it. Now, what is k? Between n is between 2 power k and 2 power k plus 1. So really, k is less than log n, log small n. And I have done roughly about 2k such checks. So it's 2 log n, 2 log small n. Okay, this is a very useful sort of a binary search procedure, where if you don't know the end, the range, so it means you're doubling. I start from location 1, 2, 2 squared, 2 cubed, checking until I find 2 steps. One is positive, one is negative. Then I know, okay, that is the range I have to look for now. So within that, I will do binary search. That takes k steps. And then up to that point, I've done some k plus 1 steps. So totally, my time is 2k plus 1, but k is nothing but at most log n. So that's at most 2 log n. Okay, any questions? So this is a very cute binary search. It's called doubling binary search. Okay, variation of binary search. Or if you don't know the maximum range, you can just do this doubling. Okay, any questions, comments? I mean, anybody else? Hania, did you understand the solution?
Yes, sir.
Okay, good. All right. So now let's move on to the next question. Next question is again pretty easy. I want to compute a power n. So your input is a and n. So let's think of it as I want to compute power a comma n. Okay. Again, you can do exactly like the doubling binary search. So all you're allowed is multiplication. Okay. So exactly like your doubling binary search, which I just described, you can do, or you can actually do the standard divide and conquer binary search, which is compute a power n by 2 recursively once, and then multiply the 2a power n by 2, take a square of it or something like that, do one multiplication. Or simply compute, you have a compute a square, compute a power 4, then a power 8. How do I compute them? Just one multiplication, right? From a to a square is one multiplication. A square to a power 4 is multiplying a square just once. Or a square into a square. I compute all of this. Eventually, I'll go above n because n is between, any n is always between 2 power k and let's say 2 power k minus 1. Then the moment I go to a power 2 power k minus 1, the next step I compute a power 2 power k, I might have gone beyond n here. So I need to come back to a power n. So I just capture what, from a power 2 power k minus 1, whatever else I need to compute, I just collect them all and put them together. And how many multiplications would I have done? Very similar like before, some k and another k, something like 2k, which would turn out to be order log n. But a power 100 was a good example. Let's see how I will do it. So I'm going to, and this has a very interesting connection to binary representation of n. Okay, we will see why. So suppose I want to compute a power 100. So what do? I compute I compute a square, a power 4, a power 8, a power 16, because these are all one multiplication. Then a power 32, a power 64. Then if I square it, I get a power 128, which I don't want. So I'll stop here. Okay, how many multiplications I have done? Only about 6 multiplications, which is log of 64 plus 1. Okay, because a to a square is 1, a to a square to a power 4 is 1, a power 8, a power 16, a power 32, a power 64. I've done 6 multiplications. Now how do I get a power 100? Well, I compute a power 64 into a power 32, which I have already computed. So that's one multiplication. I got 96, and then I multiply by 4, and that's so 6 plus 1 plus 1 equal to 8 multiplications. This is roughly log of 100, because log of 100 would be 6 point something. Okay, so it's less than 2 log of 100. And here is a very nice observation. Suppose I write 100 in binary. Can somebody tell me what is 100 in binary? Would be 0 for the 1th term.
1100
Ooh, that much is it? 1
Yes,
1
sir.
0 1 double.
100.
Is that what it is?
Yes, sir.
I thought I have too many digits here. Let's see. This is 4, 8, 16, 32, 64. Yes, okay, good. Exactly. Yes, that's 100 in binary, right? Now, how many ones are there? So this represents 64, this represents 32, and this represents 4. So those are the terms I'm doing. So the number of multiplications actually, you can verify, number of multiplications to compute a power n, this is a very nice, would be log n, maybe log of floor of n, right? Take the log n, round it down, plus number of ones in the binary representation of n. Actually, there is a -1 as well. This is an interesting theorem you can see from this description. So why? Because to go from a to a power 64, you made log n multiplications. Log of 64 is 6. No, log of 100 is 6 point something. So when I round it down, it's 6. So you get 6 multiplications to get to a power 64. And then how many ones are there? 3 ones are there. So I do this 3 multiplications, which actually -1, because there are 2 multiplications. Here is a multiplication, here is a multiplication. In any case, it's at most conservatively 2 log n. Okay, the idea is the same. It's very similar to this doubling binary search tree. You want to get to a power 100, I keep doubling. You want to get to 100, I keep doubling. 1, 2, 4, 8, 16, 32, 64. But then I don't want to double to get to 128 because my goal is 100. So now it turns out you have already collected all of these a power, various powers of 2. And if you pick wherever the binary representation is 1 and multiply them all, you get your a power 100. Okay? So it's one cute way of doing, again, using binary search. But I think people have also done something like compute a power n by 2, compute a power n by 2, and multiply them. That is like t of n by 2 plus 1, which is also has a binary search flavor, running time, order log n. Only thing is, if n is even or odd, you need to pay attention carefully. But this gives you a much more precise bound for this algorithm, how many multiplications it's taking. Okay. Any questions or comments? Okay, so these are all very interesting variations of binary search. Okay. I mean, if you're interested, one can do a whole problem sheet on binary search, some 10 questions. Okay, lots of fun problems. It's like binary search is like a puzzle anyway. Yeah, I'm just sticking to few questions every time just to make sure that people actually will attempt and do them. So the next question says, given some parenthesis sequence, I want to check whether is it balanced. Meaning that every open should have a matching close bracket. So the part A says that I just count. By the way, this is a very nice standard interview question. And people say, I count the number of pluses, opens, and number of closed, and if they are equal, then it's balanced. Otherwise, it's not balanced. Is that correct? Hopefully, most people answered this question. Anybody wants to tell me? Maybe not Vijaya and Hania, but somebody else. Reshmi?
Sir, whenever we can put it on a stack, whenever we are able to.
Wait. My first question is, I count the number of opens and number of closed, and if they are same, it's balanced.
We cannot.
Is that correct or not? Is that algorithm correct?
We cannot say it can be balanced because a closing parenthesis can happen at some other places also, sir.
Right. How do you argue that it is not correct? First of all, this is a formal, logical, mathematical question, right? So I give you an algorithm and you say it's not correct. How do you argue that? How do you say that this algorithm is not correct?
Maybe by substitution, by checking one by one cell, putting onto the stack and finding out whether we are able to pop.
You are giving me a new algorithm.
Okay.
How do you even say one algorithm is wrong? I will come to the second part later. That's the new algorithm. Anybody else maybe? Given an algorithm, how do you say that? How do you formally prove that the algorithm is wrong?
Maybe by contradiction, sir.
Yes, exactly. Be more specific.
Give a counter example.
Exactly. Give an input where the algorithm will say yes, but the actual answer is wrong, or the opposite. Okay, so always any mathematical statement, if you want to show it is wrong, you have to give what is called a counter example. So that means you provide an input on which you say this algorithm will say yes, it is balanced, but actually it is not balanced. The algorithm will be wrong. So can you give me a counter example, Reshmi? So give me an example where the number of opens and closed are same. However, the bags.
Actually, it was there in the question itself.
In the question itself, I know. I have given it. So it was there. Give me an example with just 4 of length 4. Give me
open. Closed. Open, closed.
Sorry, open.
Closed. Open, closed.
Okay. So here is a sequence where the number of opens is 1, 2, 3, 4, and the number of closed is also 4, but it is not balanced, because if I try to balance this, right, this will match this. No, this will match this. You can actually give it your this will match this. This will match this, but this one has no open match. Okay, so again, I think you all got it, but I want to just say formally, to say that some algorithm is wrong, what the way to do it is to give an example. Give an example where the algorithm will say in one way, but the actual answer is the other. Okay, so here is an example where the algorithm will say yes, it's matched because I've counted, but it is not a balanced sequence. Okay, this is again I've tried it in interviews several times, and quite often people get into this trap and say, "Oh, just count, and if they are the same, it's okay," and that's not correct. Okay, but yeah, okay. Now, Reshmi, you are giving me a correct algorithm. So, what is the algorithm?
Like whenever we find open parenthesis, we can
Yeah,
push it onto the stack.
right. And
And so whenever we are finding a closed parenthesis, we pop it out.
yeah,
Not
and when is it balanced? When is it not balanced in this algorithm?
when we have the stack empty, sir.
At the end, when the stack is
At the
empty,
end, it's
it's
empty.
balanced. Okay. When is it not balanced?
When we are left with the parenthesis in the stack.
Is that the only time it's not balanced?
Or when we don't have any
Okay, let's just break it up what you just said so that we have a complete algorithm, right? So what we're going to do is push into stack when we see an open bracket. So we just basically read the input as we go down. Pop the open bracket, pop an open bracket when we see a closed bracket. Okay. At the end, if the stack has something, stack is non-empty, then not balanced. Is that the only time it's not balanced, or are there other situations where it won't be balanced?
In the end, you see a closed bracket, but there is nothing in the stack to pop up.
Correct. Not even at the end, even in between.
Yeah, okay.
Even in between, you're saying, hey, I'm seeing a closed bracket, so pop from the stack, but stack has nothing. Then you say you have a problem. Right? So that's also a situation where it's not balanced. So push into stack when we see open, pop and open when we see closed, and at this point, if stack empty, then you report not balanced. Right? At this point, even at this point. So whenever I see an open, I push it in the stack. Whenever I see a closed, I look for something in the stack to match it. If there's nothing in the stack, then I know it's unbalanced. And then at the end, stack still has something, it's unbalanced. Okay, so that's a clean algorithm. So you can write a program, test. So for example, if it's something like this, what happens? I push this into the stack. the stack will have two open brackets. Then I see an open close bracket, so this will be gone. Another close bracket, it's gone. And I see a close bracket, nothing in the stack, so I know it's unbalanced. Okay. So in fact, there is even a much simpler algorithm, not even using a stack. One scan, not even using a stack, using some constant space, one can do it. Anybody knows?
Or you could like, this is just an idea, you could like reverse the half of that is the given thing, and then you could check whether the first half and the second half the characters match. So if they match, then that shows that this is balanced. If they don't match, then it's obviously not balanced.
No. But they have to match proper. What does match mean? That's what we are trying to do using stack, right? You don't know what matches what, and that's where stack helps. So the first half, the second half doesn't necessarily help, because even in the first half, maybe you've closed everything, and then the second half is opening something fresh. So there are all these issues there. So this simple observation is the following. At any point, number of opens is greater than or equal to number of closed. Number of open parentheses is greater than or equal to number of closed parentheses. Because if you have more closed parentheses, then you have a problem, because you have not even opened it, so you cannot even close them. Okay, so this is a very simple observation. So this is what you just count, and you just check this at any point of time. At the end, number of opens is actually equal to number of closed. But any intermediate point, it should be greater than or equal to. That's all. You just verify this. If this happens, then it's balanced. Otherwise, it's not balanced. And that's something very easy to check. So what you do is, you remember the difference, number of opens minus the number of closed. Okay, so keep track of is one number. And ensure greater than or equal to 0. So just like stacks, what you do is, whenever you have an open bracket, so you maintain one counter, just one counter, not even a stack. Whenever you see an open bracket, increment that counter. Whenever you see a closed bracket, decrement the counter. That's it. If the counter gets below 0, you have a problem. If it remains greater than or equal to 0, no problem. At the end, it should become 0. That's all. So the algorithm would be maintain. So verify this. Maintain a counter starts with 0. Increment with open bracket and decrement with close bracket, and if negative at any point, unbalanced, and if greater than 0 at the end, unbalanced. Else balanced. Okay, so it's a So quite non-trivial, and you have a very good use of stack, but you also realize you don't need stack. And it's a, again, a nice interview question. You can test question, anything you can ask. It's a good use of stack, but you also realize you don't even need a stack by just maintaining this observation. Okay, any questions, comments? So I'll leave you with one other question exercise to think about. And okay, I mean, here's something you should know. So if I think of number between 1 and n, it's all variations of binary search. So, and you have to find the number by asking me questions. Okay. So how many questions? The goal is to minimize the number of questions, and how many questions do you need, and how would you ask? It's the same. I'm just twisting binary search here and there. So it's the same kind of a binary search. So there are multiple ways in which you can do binary search. Okay, anybody? So
This is exactly what you discussed just now. Maybe 1, 2, 2 square, 2 cube. Keep asking whether it is equal to this.
yeah, but I've given you the boundary anyway. So, and I'm asking, use the standard binary search, right? You can do 1, 2, 2 square. Yeah, okay. Or if I have to just do the standard binary search, what do you do? Start with n by 2, right? Yeah. So you ask, is your number between n, is it greater than or equal to n by 2? Depending on the answer I give you, you ask the half of the other range or this range, right? Which is standard binary search. So how many questions would you need?
Log n.
Log n, right? Because standard binary search. So you start with, if I'm thinking of a number between 1 and 1000, you ask, is it less than or equal to 500? If I say yes, you ask, is it less than or equal to 250? Otherwise, you go to, is it less than or equal to 750? And then you do this binary search. And so you're reducing the range by a factor of 2 all the time. So it will be log of n. Okay. But here is the interesting twist. Okay. Very nice puzzle. What if I'm allowed to lie once? Okay, so maybe one answer, I don't know which answer is a lie. So you don't know. But I'm allowed I have a budget of one lie. Can you think of a very simple fix? And then we'll come to some complicated fix. So I think of a number between 1 and 1000. And you are allowed, by the way, you're allowed to ask only yes or no questions, right? That's what. Otherwise, if I'm allowed any question, you might as well ask what is my number and I'll give you. Okay. So you're allowed yes or no questions. And one question, you don't know which one, you cannot believe my answer. So can you just think of a very simple fix so that you still can guess the number in order log n time? Hania, I think, has done that. Hania, remember the solution?
Yes, so we do ask a question.
You
So
what?
we ask a question,
Hmm.
yes or no. Since you are allowed to lie once, we ask it another time.
Okay, the simple fix is that repeat every question once. Right? So you ask, is it greater than 500? And I say yes. You ask the same question again. If I say yes, good. Then it's the truth. Because if it's a lie, then two lies. I'm allowed only one truth, one lie. So you can move on. Is that good enough? Did you get the answer? And does it make sense? Or
Yes, sir. Yes, sir.
no, but there is still some problem.
No, we
How
are
do you
allowed to
know?
lie only once.
Yes.
How do you
So
know?
the next time the answer if it is no, we are able to find out like they have lied already.
Okay. But do you have enough to proceed is the question, right? Vijay, you going to say something?
For one question, if I get two answers, at that time I can stop
Wait.
repeating the question, I mean.
You mean
Because,
if I get two different answers, you mean?
yeah.
How do
After
you?
that, I don't have to repeat the questions, right?
Very nice.
Because,
That's true. That's true because I have done my lie. But
yeah.
obviously, I will give that two different answer only at the end. Okay. Because, but
But it's possible that first answer was right and the second answer was wrong.
okay, let's say my goal is to get some order login. Okay. So, is repeating every question twice good enough? You're saying you don't even have to repeat twice, especially if you get opposite answer once, then I know I've lied. After that, I don't have to repeat. That's good. Yes. Okay. But I'm saying there is still one more thing I need to resolve.
What if the first time the answer was correct and when I repeated the answer was wrong?
Yeah, you don't know which one is right,
Yeah.
which one is wrong. So what do you do? So you ask, is it greater than 500? I say yes. Then you repeat, is it greater than 500? And I say no. So you don't know which one is the correct. So what do you do? Hanya?
You ask the question again.
One more time. Ask one more time. That's it, right? So then you know which one is right. So I hope people are with me. Something like a 3 log n solution is simple. Ask every question 3 times. Since I'm allowed to lie only once, these are fun questions to, if you have a very advanced students who want to get something more interesting, you can play all these games. Okay. So that means what I'm saying is if ask every question 3 times, and again, Vijay, you made an observation that if I'm getting both answers the same, then I have not lied, so I don't have to go to the third time. And the moment I get two different answers, go to the third time. But after that, I don't have to even repeat because I've finished my quota of lie. Okay, so if you think about it, this is sort of like at most 2 log n plus 1. You can catch me. Right? Every question, repeat twice. And I answered them same, then you keep going. Maybe the last one I answered differently. You may have to ask one more time and you'll be done with it. Now, there are a lot of really open directions if anybody is interested. Question 1, can we do better? This has a relation to error correcting codes because in coding theory, it's sort of building redundancy. Think of it as a binary encoding I have. There are login bits, but suppose one of this is corrected, what sort of redundancy I need to add? So can we do better? This is first question, and the answer is yes. There is log n plus, I think, order log n solution. Question 2, what if there are more lies? That's a more complicated question. Yeah, so if you have a student who wants to learn something more, want to do internship or pursue all this, something, I have done this with people wanting to do internship. I said, okay, here are some papers to read. It's a very cute, nice question, very fundamental, basic binary search. We're just doing some twists and turns, and I'm learning some interesting algorithms. And it also has some applications in error correcting codes and so on. Okay, there's so much one can do with just binary search itself. There are lots and lots of variations. Okay. Okay, so anything else? So this is all about the first week. All we did was some binary search, and I set the stage for heaps and balanced search trees. The second week, we actually went deeper, did the solutions for heaps and AVL trees. Third week, which would have been released just yesterday, I have done more balanced binary search trees, more different kinds, union find, suffix trees, and things like that. None of this, I would say, is complete. So don't, it's just more of a quick refresher. You need to augment with some more reading to understand those techniques better. But if you are happy with the overall revision, this should give you a good picture. And then the next week plan is for me to now move on to design and analysis of algorithms and do some similar kind of a refresher with some motivation questions and things like that. Okay, so hopefully you all looked at the second week videos and also attempted the problems. I think the deadline has been pushed by a few more days. I will do the second week problems next week, but please do attempt them, look and submit the solutions. Okay, any questions, comments, anything on the problems or in the videos? Okay,
This discussion session is more useful actually. We are getting more ideas.
Okay, good. Yeah, and you should also come up with more questions, comments on the videos as well, so then it can be more, you will learn a lot more. Yeah. The speed, the pace of the videos are okay? Are they too slow, too fast, or just about right? Because if it's too slow, you have a way of reading, listening to them fast. I'm sure there are technological solutions. Yeah. Yeah, and this is a course again. We just really need to motivate them to interesting directions for people wanting to learn different things. There are so much there. It's like a lot of puzzles, and it's a problem-solving course again. Yeah. Okay, so if there are no more questions, then I will stop here and see you next week. Okay, so no questions, nothing. Okay. And I'll look at the problems, answers. I hope you all submitted. Please do submit them. I mean, that's the way you will learn, and you will even get any kind of a feedback for your learning. Yeah. Okay, I'll see you next week then. Bye for now.
Thank you, sir.
Thank you, sir.
Okay.